Welcome to Hot Chips 28. Session 5. Interconnects. Microns to kilometers.
We're starting off today with a paper it's going to be presented by Mu-Shan Lin on a on-package interconnect that dissipates just 62 femtojoules per bit transmitted. Mu-Shan is a technical manager at TSMC. He's been working 10 years since getting his master's degree at the Natural Zhongtong University of Taiwan. You're up.
Thank you. Okay, thanks for Chairman's introduction. Okay. Should we get started? Okay, here we go. Good morning, everyone. My name is Mu-Shan. I come from TSMC. Today, I would like to introduce a 16-nanometer, 256-bit wide, has a total bandwidth of 89.6 gigabyte per second. This in-package interconnect adopt 0.3 volt swing and with 0.062 picojoule per bit, the I/O power efficiency in info packaging. So here's the outline of this topic. I will go through the motivation. Will basically go through the potential application of the in-package interconnect, and I will also show what package we choose as our package solution. And after that, I will show some design background about our advanced package solution, and also the low power design concept that we already published in 2013 VLSI. And start from system architecture, circuit description, I will show the experimental result, and finally is my conclusion. So for the in-package interconnect, the link is named by TSMC as Leaping Con, which stands for the low voltage in-package interconnect. As you can see from the broad diagram that we used to integrate multi-chip on the PCB board. And right now with the package technology advancing, we can integrate multi-die into a single package chip by what we call the in-package interconnect. There are three possible applications that we adopt. We think it might benefit from the in-package interconnect. First, for the high-performance computing, we know that the large die size may have yield concern. For second one is the in-package memory is a higher level cache possibility. The third one is a heterogeneous integration. We believe that it might be a thinking to separate the critical block like SerDes into a mature process, but only migrate the computing unit to the most advanced technology to achieve great PPA. So the first one is high-performance computing. As we know that multi-core CPU always require large die implementation, but building a large die is quite difficult and very costly. Since the yield may go down, it's potentially as the large dies get large. So this reference work shows the chip of this work is around 20 by 30 millimeter. And we wonder that can we separate the multi-core. The work of this chip is a 16-core processor. If we separate the multi-core into 4 chips, with each die has only 4 CPU, so that the die size can be cut down to 5 by 15 millimeter. Okay. So another application, what we call the in-package memory, IPM. The reference paper shows that with the additional memory hierarchy between the off-chip DDR and the on-chip SDRAM, that the reference paper shows that it can save the main DRAM bandwidth by 16%. And as compared to the off-chip DDR, it also require only smaller capacity, but can achieve higher bandwidth and also faster latency. Besides of that, the DRAM process is more cost-effective than EDRAM. And more than that, the no TSV can allow smaller die size, fine pitch RDL, and shorter trace between the AP and in-package memory. And shorter trace can enable the termination this I/O to reach the power further. So this slide shows the memory interface development trend that from TSMC 2013 OIP forum. Based on the development trend for the white box application like this, we wonder that can we make a more compromised solution in terms of power, bandwidth, and price. For example, we want to create a higher bandwidth than YIL2, but lower cost and lower power than HB and HMC. So this slide shows to achieve the in-package memory application with low power target. We choose a fan-out wafer level package as our package solution based on following advantages. So it has ultra fine pitch RDL and ultra thin package to have smaller form factor. And also, no TSV can ensure the smaller die size and reach low cost as well. And as a result, it was suitable for a smartphone, tablet, and wearable devices. So this slide briefs the advantage of one of the fan-out wafer level package that TSMC has provided, which is called InPhi WLP. Besides, not only the more pin count are acquirable with InPhi, even with a smaller die size, the high-speed interconnect also has following electrical advantage, including the lower parasitic resistance and the lower substrate loss. And you also achieve better thermal behavior due to the smaller form factor. So based on the previous discussion, here is our project target. We actually want to demonstrate an in-package interconnect for the in-package memory application and adopt in InPhi package. In the meantime, the less capable the memory process is also considered. And we want the deep pin count to be as transparent as possible, which means it needs to be as low power and low latency in small area as possible. And we set the per pin data rate to higher than YIL2, which is 2 gigabit per second per pin, and to achieve the overall 64 gigabyte per second total bandwidth. And to reach low power, we need power efficient I/O, and to take care of the cross-die timing calibration, we need a timing calibration scheme to take care of the cross-die process variation. Okay, before our start, I was spend little time to go through the design background. This slide shows the TSMC InPhi side-by-side structure. As you can see, there are two kinds of bump adapted, including the first one is the die-to-probe bump, which has a smaller pitch and higher density. And we use that only for the high-speed interconnection. Another bump is a die-to-probe bump. The die-to-die bump has a larger pitch and also only responsible for power ground and some direct DC access pin. And overall, 560 micrometer of the package height, including 3 layers of RDL and also the BGA ball height are achieved. So the following 3 pages, we actually go through the basic concept of a low power design, what we have published in 2013 VLSI. The first one, we want to create a reduced power driver, which means we lower the swing with lower VDDQ, and we also remove the termination, so that the driver only consume dynamic power and consume power from 0.3 volt. The second one, we want to create a reduced power receiver for the interconnect I/O. The clock sense amplified type of the receiver front end is created. With this sense amplifier, the incoming data can be captured just on the I/O pad, so that we don't need to spend power for the balancing purpose buffer for each DQ. So that is why we can save the power. in the receiving path. But as you can see, remove the balancing purpose buffer will bring out to another design requirement. We need the PL, discrete PL or discrete DL to cancel out the fan-out class 3 latency. And we also remove the near-end termination, so they only consume dynamic power as well. So can see the memory process is less capable. We also like to make a simplified design in DRAM by getting rid of the PL DL block here and move to the SoC side. We believe that it will be implement more efficiently with logic process instead of the memory process, so that we can also reduce the power and area from the memory die. So here, this slide shows basically the top architecture of our work. An overall 64 GB per second total bandwidth is a chip which is composed of 256 DQ, with each DQ operating at 2 gigabit per second as our target. And each DQ and DQS are bidirectional to save the pin count based on the speed target. And the 256 DQ is partitioned into 4 channels, and each channel is partitioned into 4 subchannels. As you can see, each channel also arrange one CA channel to take care of the command address for the memory array, and each channel also implement a subcalibration channel. The subcalibration channel is used to take care of the close die process variation. Okay, so each subchannel we design is a modular-based design, so they can make it easy for scaling and with physical balance. So there is no, you can see, no PL or DL blocker in the memory die. So the memory die rely on the only clock source from SoC through the CK, which is transmitted within the sub-CA channel. So this slide shows the sub-DQ channel architecture. As we talk, each sub-DQ channel contains of 16 bits of DQ, and they are served by addition one differential clock DQS, and also along with 2 bits of per byte DMI. The DMI combine the coding, including the data mask and data bus inversion. The data bus inversion, we think it can help, based on our evaluation with the data mask inversion, it can help to reduce 50% of the decoupling cap for the SSO noise control, which is important for the wide bus and high-speed application. So we know that the timing calibration scheme is important for link reliability because the different die may have a different process variation. So there are 3 DL proposed in this work. For the first one, for the right path, the DLTS will actually discrete the extra class 3 latency here in memory die. 3D are only implemented in SoC die. The DLTS discrete this turn and make sure the data can be captured on the I/O pair with the center and line phase relationship. Similar concept to the repass, the DLR is also implemented in SoC side, will discrete the class 3 latency and push additional 270 phase degree to make sure the center and line relationship between the data and DQS. But even though the data can be captured by the I/O, but there's still an asynchronous clock domain issue between the SoC die system clock and the incoming DQS. Conventionally, we used to implement a receiver FIFO, but it will cause additional latency and hardware overhead. So that's why we propose the third DL, what we call a DL RPT, purpose to synchronize between the SSCOK to the incoming RDQS. Okay, this slide shows how I mentioned about the subcalibration channel architecture. 3DR are implemented in this subchannel. The third DL, what we call the DL-RPT, will highlight as a blue color from this diagram, which is new from our previous work. Since the incoming DQS will be stopped when idle, will be getting when idle to save power, so we create a replica RTQS with free running clock, so that the DL-RPT can help to adjust the phase of SSCLK to align with the incoming RTQS to do the phase align purpose, to take care of the asynchronous clock issue. And based on this, this timing calibration scheme, with this timing calibration scheme as compared to the memory interface training protocol, you can save the re-latency, and also it will be easy to implement and shorter lag time to be less than 1 microsecond. And this scheme is also scalable because one channel has one DL for each one, and the DL lag result will be broadcast to each DL in each subchannel. Okay, this slide just highlight we know that the latency cost will actually degrade the system performance. So we summarize the latency information in each part. And with the DL-RPT, by removing the receiver FIFO, right now we can reduce the latency to be less than 1.9 times of clock cycle in the receiving pace. And the latency is design dependent, depending on your architecture, whether it's your serialization ratio or whether you implement the DPI or not. So we know that the timing calibration scheme can help to calibrate the process variation when power on initialization. But we know that the temperature may drift during normal operation, and the temperature drift may induce unexpected timing variation and degrade the system performance. So we come out a temperature drift monitor scheme by leveraging our DL architecture. Each DL TSMCs will be enabled for each 1 millisecond. And the DCDL will sense the temperature drift and reflect to the new lag code. And our algorithm will check the code difference between the new lag code and the original code from power on initialization. And alert will be issued once the code drift is our design tolerance. So this slide shows the path plan across the die. As you can see, a compact path plan with a perfect match trace length over 256 DQ bus are achieved. You also achieve high routing density that it takes only 10 microseconds for each RDL routing. And the higher routing density can also make the trace length shorter. So the following two pages will go through the boundary scan strategy. So we adopt the boundary scan flow that is compatible with IEEE 1149.1 that we co-works with mental graphic. So each die, either SoC or memory die, will implement the self-tap controller. And the boundary scan strategy at KGD level is used to test because we know that the die-to-die bound the pitch is too small to probe. And at KGD level, the boundary scan will help to check the open show of loss on probe I/O. At KGS level, once the interconnect RDL are built, with each die built-in self-tap controller, now we can use the test pattern will be import from the test pattern will be import from the tap controller of one die, then we will ship the data into the unprobed I/O and captured by another die of the unprobed I/O and shipped out by another tap controller of another die. We can use that to test the interconnectivity and also capable of per-pin diagnosis. So this slide shows the package die photo after info package from the BGA board side. As you can see, the fan-out is to get the required SS BGA baud number, and each KGS chip only occupies 7 by 7 millimeters. So the following 3 pages will show our Shimu test result. For the first one, at KGD level, we test the SOC loopback bit. The high-speed data will be transmit and propagate to the unprobable high-speed I/O and turn around into the bit circuit to check the bit result. And we sweep the logic VDD versus frequency. As you can see, a proportional trend is obtained, so that the performance right now is limited by the logic power, which is logic power. And you can also see up to 2.8 gigabit per second are achieved under nominal VDD of 0.8 volt. And the testing is based on 256 DQ toggle with DBI enabled and PRBS pattern. The second one, for KGS Shimu test, we test the SOC to memory die right bit circuit based on the same operating condition. And we also sweep the logic VDD to the frequency. As you can see, a pretty close result as compared to the KGD is obtained. We can say that the timing calibration scheme works stable, even with good margin across die. And also, the performance is still limited by the logic timing, even consider the interconnect RDO. So up to 2.8 gigabit per second data rate is achieved under KGS testing. So we want to, the third Shimu test result, we want to test the link reliability for the interconnect I/O, especially focus on the VDDQ with wide range accommodation. So we additional sweep the VDDQ for the I/O driver versus frequency. As you can see, under the VDD equal to 0.8 volt, we can still get 2.8 gigabit per second from VDDQ sweep from 0.5 volt all the way down to 0.15 volt. So 2.8 gigabit per second still work under VDDQ equal to 0.15. So this slide shows, as we know that the 0.3 volt are the key to reach the low power, but the 0.3 volt also make the power more sensitive to the SSO noise, especially for these kinds of wide bus and high-speed application. But the I/O right now is unprobable because the pitch is too small. So we come out bit engine-driven iProd as an alternative to check the signal integrity on bus. As sweeping the DCDL code in terms of timing in the X direction, and also sweep the reference voltage, which is for the clock-based sense amplifier in the Y direction. Then we can overall to plot the I diagram. And the diagram shows we have 250 millivolt I high and 0.84 UI I width. Besides, you can see the original capture point that we read from the DL lock code result has a slightly timing shift due to the unbalanced physical skew. And also, we found that the SSO noise from ground is worse than from power, indicate that we may need to add more decoupling cap to reduce the SSO, if necessary. Okay. So this slide shows a power breakdown summary that is based on the simulation result with a worse toggle condition. So if we consider only one single bit of single NIO, it can achieve down to 0.062 picojoule per bit. But when you consider the entire system, the I/O, the efficiency, power efficiency for the I/O will be degraded due to the other sideband signal like DBI or command address or DQS and so forth. So additionally, it also achieves low power efficiency for in terms of whole file down to 0.424 picojoule per bit. Okay, this is my conclusion. And in-package interconnect for the in-package memory application in InFO package has been demonstrated by TSMC 16 nanometer FinFET process plus InFO package. And Overall, 89.6 gigabyte per second total bandwidth is achieved under 256 DQ, with each DQ operating at 2.8 gigabit per second. And we also adopt a 0.3 volt swing. It also achieved, under 0.3 volt swing, also achieved low power efficiency for the I/O, which is 0.062 bit picojoule per bit. And in terms of phi, it's 0.424 picojoule per bit. And as low latency as possible is achieved. And for the 0.3 volt signal integrity on the unprobed I/O has been clarified to have 0.84 UI I width and 225 millivolt I high. And to deal with the cross-die process variation, we can see the proposed timing calibration scheme by DL is work unsettable with good, at least 40% timing margin. Okay, so this is right now my presentation today. Thank you.
Thank you very much. So we have time for a few questions.
Ken Chen from Xilinx.
So we'll start with the left first. Come down to the microphone if you have a question. Okay, we'll start on the left here.
So Ken Chen from Xilinx. Actually, very good work. Just some clarifying question. So in your power, the other side is DRAM. You're using 16 FinFET to emulate DRAM, but DRAM process usually much slower. So what's the power efficiency if you are using the true DRAM process? Have you estimated that?
Yeah. Besides that, we have no data actually, but currently we just use SRAM to mimic the DRAM process. And for the real power efficiency, if we adopt the DRAM process, we don't have the data actually.
And you believe the 0.3 volt will work in DRAM process as well?
Yeah. Actually, we have one work that is ongoing, and then currently we adopt 0.3 volt.
Second one is, I'm not sure the DOO repeat to do domain crossing that you quote is really working because you slave the system clock to a DRAM clock. But in reality, you have multiple DRAM channel. You actually need to slave the DRAM clock, the receive clock, to the S clock. So I'm just not sure when you are quoting eliminating the FIFO for domain crossing using the DO technique. Can you comment on that? If S clock need to be unified against assuming two DRAM channel, two memory channel, does that technique still work?
You mean each subchannel of SOC talk to each subchannel of memory, and they are
assuming you have two DRAM memory channel to talk to one SOC. Does that work?
We assume that each channel operate independently.
Okay.
And each channel has their self clock domain. There's their one clock source of CK.
But I'm saying, do you believe that's reasonable for a system from a system perspective?
Right now, we work with our one of the vendor for memory process. We based on that structure actually.
Okay, thank you.
Thank you.
Okay, the question over here now.
Thank you. One of the questions answered. This is Farid Saleh from Toshiba. I just have a quick question. The PRBS that you said you use, which PRBS was 2 to the 7 or something else?
Oh, it's 7 electrically.
Thanks.
Okay, next
Yes,
question.
Brian Holden, Can-Do Bus. There's been some discussion in the HBM world of adopting an interface like this. And in their case, they're looking a little bit longer. That 550 micrometers is so short. What would you say this interface would look like if it was 3-4 millimeters long?
Can you repeat the last statement?
Yes. What would your interface look like if the link was 3 or 4 millimeters or 5 or 6 millimeters long instead of the half millimeter?
Okay. The driver for this case, we actually design for the target of 1 millimeter. But the plasticity for info is small. But even count to 1 millimeter trace density around 20 femtofarad only.
So what would this link look like if it was, 4 millimeters?
He's asking what would it look like if it was 4 millimeters long.
Oh, 4 millimeter would need a larger driver for the I/O. Yeah, definitely. But it requires larger power, but using info has an advantage of a smaller pitch of a die-to-die. So that we can have a shorter trace and we can reduce the power for I/O. That is the basic concept. Yeah.
Great, thanks.
Okay, thank you.
Thank
So our
you.
next talk, we move from the, let's thank our author again. So for our next talk, we move from the millimeter scale to the kilometer scale. Speaker is Radhakrishnan Nagarajan. He is the CTO of Optical Interconnects at InPhi, and he is a fellow of the IEEE, a fellow of the Optical Society of America, and he's been doing optical interconnects for over 20 years.
Okay. I'm more used to giving this talk to a group of optical engineers and scientists, so I'll try my best here in the Hot Chips conference. This work was done in conjunction with Microsoft Corporation. I will start off with the state of the data center interconnects and why this particular interconnect suits the architecture that Microsoft has in mind. My co-authors are Tom Isenhuth and one name's missing, Tom Isenhuth and Mark Filer from Microsoft. All right. First, sort of a primer on where the data center interconnects are headed, where they are. This slide is a veritable soup of 3-letter acronyms. You have to sort of forgive me. I'll try to go through them and then sort of explain where they're headed. There are generally 3 types of interconnects, largely based on distances. First is simply the server to the top of the rack switch. They're fairly short. And servers are just transitioning from 10 gigabits per second to 25. 25 gigabit per second ports are not in deployment yet. And in the 18-19 timeframe, or a little later, they would transition to 50 gigabits Ethernet data rates. When this happens, you will have to move from what is it today, which is a direct attached copper cable, to what's called an AOC, an active optical cable, or an SR, a short reach optical cable. That is the dynamics within a 19-inch rack and 6 foot tall. And then the next dynamic is within the data center, between racks, between switches. This type of interconnect could go as far as 1 kilometer or 2, given the size of interconnects, given the size of data centers, especially in North America. And 40 gigabit Ethernet is widely deployed. It's transitioning to 100 gigabits per second. A lot of equipment going in today, 100 gigabits. And you have another set of acronyms here. They all refer to different types of optical interconnects. You don't have to get lost in this acronym soup. And this is not 28, by the way. And that's in the 18-19 time frame. These would switch to between 17 and 19, from 200 to 400 gigabits. This is within the data center between Tier 1, Tier 2, and Tier 3 switches. And then there's a whole host of interconnects between data centers which are becoming important. When you cannot build a contiguous data center which is large and serves your needs, what ends up happening is you build a series of data centers, but you still want to maintain the latency to a predictable number so that you can treat them as a a distributed data center. And that's where the link that I'm going to talk to you about comes into play. Today, between data centers is 10 gigabit per second. And anything beyond 10 ends up looking like a transport platform, which the data center, people who are deploying data centers do not want it to look like. So this is a typical hierarchy. You start with a server. You go to a top-of-the-rack switch. You go to an edge switch. You go to a router. You go to a transport box. You go to the internet, and repeat the process at the other data center the other way around. Not a great architecture today. And as you are well aware of, leads to unpredictable latencies. You can't actually make these things perform data center and data center to operate as a contiguous unit, especially when you have transport boxes in the middle. What Microsoft essentially wanted to do when we started working with them was to short circuit this. What happens to two data centers if you can actually connect them at the edge switch? Now you're not routing, you're switching, and you're connecting two switches with a lot of bandwidth. And what that allows you to do is now your packet's a lot more predictable, a predictable latency, and within your design parameters, you can interconnect two data centers over some distance. And that distance turns out, in this case, about 70 to 80 kilometers. 80 kilometers was the target that we were shooting for. Now the question is, how do you actually build? What we're actually building is actually a transport box on a module this big that would plug directly into a switch. So the switch can't tell the difference if it's talking to the switch next door or it's talking to a switch that is 70 kilometers away or 50 kilometers away or 20 kilometers away. And that was the challenge. So what we ended up doing for this particular, this is another way to slice the cake or dice the problem. The group here, the Ethernet crowd is used to this IEEE 802.3. And the CR force, SR force, and LR force, 100 gig, anything within about 10 kilometers. And I come from a world that does anything beyond 100 kilometers to 10,000 kilometers. That ends up being the domain of ITU, OIF, and most of the time it ends up being large boxes, large chassis, large carts, consume a lot of power, but they have a lot of performance. And these carts do submarine, do cross-country, they do metropolitan. And we ended up calling this gap the metro data center gap because the data center people didn't want to pay the prices of the transport, and you didn't need the performance of transport at 10 kilometers. But what you still needed was a link which looked like a transport link with two what we call EDFAs, erbium doped fiber amplifiers. I'll come to that in a moment. If it's a different crowd, they would know what an EDFA is, or maybe you do. And interdata links going up to 100 gig, distributed architectures, and what we picked up was a QSFP 28 module to see if we can actually make this link work. This is what the module looks like. I'll give you a feel for the size in a moment. Within this module, the core of the module is the Pam ASIC. We picked a 4-level Pam modulation format as opposed to an NRZ modulation format. And the output from here, the host side to the switch, was a 4x25 COWI. The COWI data is actually 6664 encoded, so it comes in at about 25.78125, I think. And then it goes to a driver and into a silicon photonics chip. Actually, the optical part of this is actually implemented also in silicon. And the laser was external, but the modulators and the photodetectors and the receivers and the transmitter, they're all on silicon photonics. And what we did was we took the 4x25 and converted that into two streams of roughly 28 gigabaud signal, which gives you 56 gigabits per second, and 2 lambdas or 2 wavelengths would give you 100 gigabit per second per module. What I'm going to do here is take each one of these separately and tell you about them. Again, it's a standard Cowie interface, and the power consumption of this module is 4.5 watts. So one of the things that become important is if we want to plug this into a switch, you better not consume a lot of power, otherwise a switch will not be able to power it. And this operates at a 3.3 volt power supply. This is what we call fat pipes between data centers look like. You have two modules, and they have different colors, one way to look at it. And then you have an external combiner, what we call a multiplexer, at 100 gigahertz channel spacing. So you can combine 40 of these modules. That's where you get to 4 terabits per second, and they're different colors. So you optically multiplex them. And the link has two, what I call OAs, optical amplifiers. Technically, the OAs end up being erbium doped fiber amplifiers. So what we ended up doing is in the optical system, on the line side, as defined by ITU, your grid is a 100 gigahertz grid. So the challenge was, how do we squeeze two wavelengths at 100 gigahertz, two wavelengths within a 100 gigahertz envelope? These two wavelengths are spaced at 50 gigahertz. So the way to think about it is you have a center frequency of 193 terahertz in which I have two wavelengths separated by 25 gigahertz. It always sounds insane, but in optical world, you can do that all the time. So you take two of these out of a module, and then you squeeze it into a multiplexer, and then you put 40 of these modules, and you end up getting 80 of these wavelengths, each at 50 gigahertz, gigabits per second, or 28 gigabaud, and that gives you 4.5 terahertz. This is the Pam ASIC, perhaps like a lot of the ASICs that are presented at this conference. Operates off a 0.9 volt digital supply, 1.2 volts analog supply. It's referenceless. It recovers the Cowie clock. And then you have a whole host of protocol, DSQ and protocol functions. And we have an internal FEC. I will talk about it a little later. And this clock and the output are in synchronization. You have a PLL at the output. The same happens on the other side. When the data comes in, we have a 28 gigasamples per second ADC. And then you have a DSP chip, and then you need a FEC decode, and you need a framer, and then you have to do pre-FAC bit error rates, post-FAC bit error rates, and we also have a PRBS generator, and then you have a Cowie transmitter that talks back to the host. It's a CML driver. It's an analog front end with a digital back end. CMOS back end enables a wide swing range. You can have an output up to about 800 millivolts differential. The output side, on the line side, is clocked at 14 gigabits per second, and the input is, it's a two-phase or a four-phase clock, or a quadrature clock. The ADC has a 7-bit resolution. And you have a CMOS path with regulators, multiple regulators for power rejection, independent domains. The transmit side has a three-tap FFE. On the receive side, you have a multi-tap FFE DFE, which is also used to calibrate the DSP. It's referenceless, and the clock is recorded on the Cowie side. This is the Mach-Zehnder modulator, which is built in silicon. For those of you who do not deal with silicon photonics all the time, it is actually, the way to think about it is a depletion mode capacitor. And when you apply a signal voltage to it, it changes the carrier density in the active region, which then modulates the light. It modulates the index, which then is placed into a Mach-Zehnder configuration that modulates the output. The same modulator was used for both an optical eye. You can get an NRZ or a PAM4 optical eye. You don't really have to change the modulator structure. The Pam ASIC has a MSB LSB output, so you can get a 2-bit DAC, is what we actually implemented in the driver. And again, power is the biggest consideration, so this was a direct coupled driver. There were no back termination, and the termination was at the other end of the modulator. And this modulator had a bandwidth in excess of 25, 26 gigahertz, depending on how deeply the junction was biased. So this is actually a modulator made out of silicon, so and sort of a CMOS process. In a silicon photonics chip, silicon does not detect light at the 1.5 micron region that I need for long-haul transport. We used germanium, pure germanium. This is one of the anomalies of a silicon photonics process running on a CMOS line, so it doesn't quite run on a CMOS line. And the bandwidth of this photodetector was in excess of 20 gigahertz. The dark current, we operated this at about a volt. This thing depletes fairly easily, and you can just bias it through your transimpedance amplifier. So it does not require a large bias voltage. At about a volt, it's under a microamp. Germanium is notorious for dark current. So that's one of the things that you have to be very careful. And one of the other things is we are growing pure germanium on silicon. There's a 4% lattice mismatch, so there's a lot of care that needs to be taken trying to grow pure germanium on silicon. But you cannot use silicon to detect light at 1.5 micron. The receive path was also polarization diverse because the incoming light is of indeterminate polarization state. If you don't detect both polarizations, you'll end up having fading. So we ended up detecting both polarizations and recombining the lights, and you have to build what's called a polarization beam splitter. It's one of the optical components that you can actually build on silicon. You split the two polarizations, and then separate the two wavelengths, and then recombine them at the end. So I have two wavelengths. This is the external filter. This is a commercial 100 gigabits per second multiplexer. The passbands typically look like these. You can buy them with a flat top. The center frequency of this particular filter was at 193.4 terahertz. And within that, it's channel 34. We squeezed in two of these lambdas, and this is what it looks like when you actually stick it into. I'll show you a photograph of what the system looks like within these two filters, and then you have another filter to separate them in the end. And these things repeat themselves every 100 gigahertz. The next one is at 193.5. So this is what the actual optical spectrum looks like. When they come out of the optical module, this is a short noise limited optical signal. A short noise limited optical signal has about 58 dB OSNR. And by the time it goes through 120 kilometers, I have two optical amplifiers. My noise limit has already gone up this far. I'm at about a noise OSNR of about 33, 34 dB. This is largely this is largely amplified spontaneous emission noise from an erbium doped fiber amplifier, like any other amplifier. It just keeps adding noise to it, but the laser output, the module output, is essentially short noise limited when it leaves the module. And this is an optical spectrum separated by 25 gigahertz. And this is the output after 120 kilometers. This is what the system actually looks like. After a lot of drawings, you actually get to see where we plugged in and what we did. For those of you wanting to know how big this module is, this is a 1 RU rack, what we usually call a 19-inch rack, and there are 18 of these modules across for this particular configuration. This is a commercial 3.6 terabit switch. I think the vendor would not mind me telling you where it came from. It is actually from Arista, a Jericho-based switch. So there's a plug for them. And you collect all these things, fibers, and then you go into a multiplexer, and then an amplifier, and you come back and you go to the next switch. This is a lab configuration. And if it's in the field, this will go in here, and at the back of it, you'll have 10, 20, 30, 40 kilometers. At the other end, you'll repeat it, and it'll come back. So that's the multiplexer, amplifier, And the fiber is a linearly dispersive element. And if you do not do any post-processing, you'll have to compensate the dispersion. And the way we do dispersion compensation optically is you put an optical fiber of the opposite dispersion, and then, hey, you get back to where you started. And that's what's called a DCM, a dispersion compensation module. You need that. So all I've done right now is I've cut 2 layers of optical transport. I've just gone directly from a switch to a next switch through an optical transport system. And the dispersion compensation modules can be placed in the middle of these optical amplifiers. Let's look at this graph first. Of course, there's a certain amount of dispersion tolerance window. You don't have to compensate the dispersion exactly, so there is some latitude of tolerance about 100 picoseconds per nanometer and about a 1 dB penalty. So this is a plot of a bit error rate versus optical signal-to-noise ratio. The 120 kilometer single-mode fiber that we used had about 26.2 dB loss. The losses vary. It depends on a number of things. Because the fiber loss isn't just fiber loss. You have connector losses, interface losses, and lots of other things. And in a practical situation, you also have fiber cuts, fiber patches. So this loss is not fixed, although it's about 0.2 dB per kilometer. It's not a very consistent number. And the data rate is 28.125, and the FEC that we have, that we call ubiquitously an IFEC, has a correction limit of 1e minus 2. I'll get into the details of the FEC in a moment. And for comparison, this is a standard KR4 FEC that IEEE recommends, and that limit is at about 1e minus 5. These are theoretical limits, and we'll have to you have to sort of allow for some practical implementations. So the way this plot is generated, you'll see channel 0, channel 1, channel 0, channel 1, meaning there are 2 wavelengths within a single module. And we measure the bit error rate for each one of them. They're fairly close. And if you were to get the dispersion compensation fairly accurately, you do not have impact going over 120 kilometers. It's not non-zero, but you have about a 2 dB impact going over 120 kilometers. So you can actually close a link between 2 switches that are about 100 kilometers, 120 kilometers apart. For the nomenclature on FEC, the way we implement the IFEC is we take the incoming data at 25 gigabits per second, usually 6664 transcoded. So the data rate is 25.78125. We strip the transcoding, and then we impose a 257, 256 transcoding, and then we put on the IFEC, which is actually an iterative code, and takes us to 28.125 data rate. So there's a data rate overhead, but it gives us a great correction limit. As you can sort of see, it starts correcting at, this is already starting to drop, so the correction limit is somewhere out here. It's sort of a nice brick wall, and the way this was measured is we use an external ONT with a straight interface into a module. We looped it back using an EDFA, one for gain and one for noise loading to get it down to the level that we wanted to measure. KP4 and KR4 FECs are Reed-Solomon codes. Okay. And, oops, oh, this is the older presentation. Okay. There was a slide in here that I was going to show you what 80 channels loaded would look like a 4 terabit system. Unfortunately, the slide is missing. I'll have to stop my talk right here. Thank you.
So we have time for a few questions. Come down to the microphones, please. State your name and affiliation.
Ken Chen from Xilinx. It's actually on your left.
Hi.
Okay. Excellent talk and excellent
Thank
work.
you.
I get questions since I'm not an optical expert, but
Sure.
I do PAM4. So what do you think about, you choose to use 2 wavelengths and PAM4 to accomplish 100 gig.
Yes.
How does that compare to 4 wavelengths and the NRZ? Have you considered that option?
Yes. The reason why we chose to, there are several reasons. One is when you have 2 data links separated by some number of kilometers of fiber, the main metric in a transport system like that is spectral efficiency. 4x25 is not as spectrally efficient unless I multiplex them at a 25 gigahertz spacing, which makes it a lot harder problem to solve. I'm sorry. They are both the same baud rate. So what I meant to say was, for a given bandwidth, for a given spectral bandwidth, I have twice more capacity in PAM4 than 4x25.
Yeah, but can you, I don't know whether optically, because PAM4, as you see, the eye actually is not even. And
yes.
I don't know how much loss you get, array loss from PAM4 compared to Gen 4 channel, for wavelengths. That's really...
That brings me to my original answer. I'm not spectrally efficient. I can only build a 2 terabit per second system.
Okay.
Right? It's all spectral efficiency. Because I have a pair fiber that's running between 2 cities. The question always is, how much can I squeeze into it?
Okay.
But your point's right. You will have a better signal to noise ratio. You will have a better sensitivity limit if you did 4x25. But given that same bandwidth, 25 gigahertz bandwidth, and PAM4 I get twice as much. And if I were to do 16 QAM, I'll get twice as much more. But then I have to go to a coherent detection. So PAM4 is a nice direct detection scheme that's between NRZ and the multi-dimensional transport constellations.
You believe this is power efficient?
Yes, in the sense that, okay, power efficient, let's back up a little. To get the eye, we're talking about equivalent eye opening. On a PAM4 system, I only have 2 modulators and 2 drivers. On a 4x25, I have 4 modulators and 4 drivers and 4 receivers.
Maybe let me explain the reason I talk about power efficient.
Yes.
If you do PAM4, you most likely you will have to do ADC based. If you do NRZ, that backend, electrical backend could be just analog based. And I believe that will be much more power efficient. I just don't know.
We looked at it. I don't think we'll come out so far ahead that it makes it compelling.
Okay. Thank you.
Thank you. Yes.
Okay, question on this side?
Jeff Becker from NASA Ames. I'm curious, your target here was Ethernet.
Yes.
What about other networks, like, say, InfiniBand? Does that work?
This particular module, although it's not widely advertised, you can put it in what's called a bypass mode. Meaning the FEC was designed as an Ethernet FEC because we removed the transcoding, so that allowed us to use that to minimize the overhead. But actually, if you had a host FEC or a host protocol, you can operate the module in the bypass mode. Not widely advertised, but you can do it, yes.
Okay, thank you.
You're welcome. Yes, sir.
One more question.
Rohit Mittal from Intel. So can you speak as to the power distribution between the ASIC and the silicon?
Optics?
Optics, yeah.
They're about half roughly. The Pam ASIC consumes about 2 watts, a little under 2 watts. And the optics and everything else is about a little over 2 watts. You add them up, and then you have the power efficiency of the regulators. It's like a 10% overhead. That gets you to 4.5, a little over 4.5 watts.
So did you have to do any kind of thermal management of the lasers to maintain the grid spacing?
For this grid spacing, yes. They are thermally stabilized. More than that, we have algorithms and structures on the silicon photonics to stabilize the wavelengths, or actually to lock the wavelength to grid.
Okay. All right. Thanks.
Okay, well, let's thank our speaker again for a great talk.
Thank you.
So our final talk is intermediate in distance, and it's on the Intel Omni-Path switch architecture. Our speaker does fabrics and switches for Intel, and he tells me that he spends half of his time on fabric diagnostics.
I'm here with Intel talking about the Omni-Path Gen 1 switch and platform. I'm the lead architect of the switch, and Vladimir Tamarkin is the lead architect of the platform. So some of the topics I'm going to talk about are the Omni-Path goals and the architectural overview, some of the switch features, a high-level block diagram, how does the packets move within the switch, packet forwarding, the switch internal bandwidth over-provisioning and benefits, the traffic flow optimization and egress port arbitration, congestion, and then I'll go and talk a bit about the innovative dense platform packaging. And the final slide will be a summary on performance. So some of the goals that we had for Omni-Path's architecture had to do with improved per port cost and power and density, trying to improve the node bandwidth, the message MPI message rate, low latency, efficient error detection and correction at the link layer, quality of service, and then scalability and a lot of factors like that. This is an overall picture of kind of an architectural view of the components that we have for the Omni-Path architecture. There's three components: the host fabric interface, and the host fabric interface is a connectivity to the compute, the service management nodes. Then there's the primary fabric, which is comprised of all the switches, and then a fabric manager that provides the central provisioning, fabric discovery, monitoring, and then also quality of service and resources. I'll do a quick step through on some of the features of the switch architecture. The switch is a 48-port switch where each port is 4 lanes. Each lane has an integrated 25 gigabits per second long-reach SerDes. Each port's capable of 100 gigabits per second or 25 gigabytes bidirectional bandwidth. Switching is done with a unicast route table or multicast route table. Each port supports 8 virtual lanes and 1 management virtual lane. Packet sizes that can be worked on range from 16 bytes to 10 kbytes. The egress port has an added feature, packet preemption for the traffic flow optimization, and I have a slide later on that will talk about how that works and some of the benefits. There's a switch management port that has an on-chip microcontroller for port 0 functions. There's an optional PCIe interface for firmware to a processor complex for firmware for fabric discovery and things like that. There are multiple I2C interfaces for firmware loading, diagnostics, upgrading in the field. The internal to the switch, the data paths and all the memories are protectable with ECC. We have a packet integrity protection mechanism at the link, at the Omni-Path link layer, and that's a link level CRC. I've got a slide that talks a little bit about that later on. And then there's also dynamic lane scaling, where a port has 4 lanes, and if a lane goes down or 2 lanes, it'll dynamically scale to the working lanes, notify the on-chip microcontroller, and from there a trap message gets sent up to the fabric manager for handling at a later date. This is a block diagram of the switch where the 48 ports are organized into 12 megaports, each megaport working on and servicing 4 ports. Each port has its own unicast route table. There's a single multicast route table that'll service all 48 ports. There's a central port or a control port that processes all the switch kind of management agent packets. And it has a microcontroller and an interface to the PCIe. So some of the key points are we group the 4 ports together into megaports and have a common logic that will service the 4 ports. This is a way to reduce wires to a central crossbar. The central crossbar contains logic and wires that'll connect the 4 or connect the 12 megaports along with the control port. There's a full unicast route table in each megaport, and that's pretty key because now there is the full route table being at a megaport. Each port has the ability in a predictable manner to be able to access lookups, no matter how big the fabric is, and as you scale, it's not going to impact latency. I'll talk a bit about how the packets move around within the switch. The packet forwarding I have a slide here that has a diagram that shows the general flow of a packet. The switch supports a packet pull architecture, and that's where the egress port, when it makes a decision on which packet it wants to send, it'll pull the packet from an ingress port and then transmit it. So if I go through the example I have here, an ingress packet comes in, the packet is written into an RBUF structure. The packet header is sent to a tag control block. The tag control block performs a series of functions, one of which is a destination port lookup. And a packet tag or a packet descriptor is formed and sent to egress ports. The egress ports will collect up these descriptors and organize them into VL FIFOs. We call them VL work FIFOs. These FIFOs are presented to a tag arbitration machine that will take a look at what's the remote credit, what's the bandwidth, and quality of service for that particular VL. So a packet request is formed and generated and sent back to the ingress port. The ingress port will read the packet from RBUF and transmit it to the TBUF, and at some point later, a packet segments are put out on the wire. The key here is the egress ports are the master. They have all the information they need to make decisions on what to put on the wire, how to do your quality of service. The congestion and all other kind of metrics are all tracked by the egress port. This is a higher level diagram of the M port, talking about the bandwidth over provisioning. As I said earlier, there are 4 ports. Each port has an RBUF and TBUF structure with the ability to write a single packets into the RBUF structure. That's the 12.5 gigabytes per second. There's 3 read paths coming out of the RBUF structure going to an M port crossbar. Each port is doing that, and that kind of shows that with the blue lines going into the M port crossbar control block. There is a 75 gigabyte per second connection to the central crossbar, and that's represented by 6 paths. These paths they're set up by 6 RMUX structures inside the import crossbar. Each RMUX structure has the ability to read a packet from any one of the 4 ports or 12 paths that are available. So then if we look at the TBUF structure, there's a single packet path coming out of the TBUF and 4 packet paths going into TBUF. That represents the 50 gigabytes per second. So the summary on the over-provisioning is there's a 3x over-provisioning at RBUF exit, a 1.5 over-provisioning at M port exit, and a 4x over-provision at the TBUF entry. So the overall over-provisioning in the central crossbar is 2.75 or 3.3 terabytes of bidirectional bandwidth. The over-provisioning is a big advantage for reducing latency variation. It improves the port bandwidth. packet performance, and then recovery time when egress ports enter congestion states and release from congestion states. So I have an example at the egress port of arbitration for, this is just one example of how the traffic flow optimization works. I have in the diagram I show packets can exist in the switch in 3 different kind of states. So one of them is they're in the ingress port, RBUF structure, or they're in the crossbar, or they're in the TBUF structure at egress port, or they're out on the wire, and that's the bottom row. Now I'll do a quick summary on the bottom row. The egress ports are going to put together packet segments, and that's 2 flits or 16 bytes. That's kind of the granularity of what they can put out on the wire. A group of 8 of these double flits are grouped together in what we call LTPs, or link transfer packets. These link transfer packets have CRCs wrapped around them, and as they're received at the ingress side on the remote end, the CRC is checked, and if there's a failure, there's a notification sent. It's a common link level replay. So that is the kind of a brief description of the packet integrity protection mechanism. So in my example here, I've organized packets and messages in 3 different categories: large messages, medium messages, or small messages, which are like the low priority, high priority, and what we call preemption-based packets. In this example, I've organized, for example, VL0 and 1 as large messages or storage-like traffic. And I've organized VL4 as a medium type messages where latency is somewhat sensitive. And I have VL2 and 3 as small messages, MPI-like compute traffic, where latency is very sensitive. In this example, I show the first packet coming down path 1. I've listed 4 paths. Those are the 4 paths into the TBUF structures. So if you look at packet 1, it currently resides in the ingress buffer, it's in the crossbar, it's in TBUF, and it's also being put out on the wire. So that's an example of a cut-through packet. But it's shortly after VL0 is being put out, or packet 1 is being put out on the wire, packet 3 shows up on VL2. Well, VL2 is programmed as an MPI compute-like traffic that has a very high latency sensitivity. So it's going to go ahead and packet segments from 3 are going to interrupt packet 1 and get put out on the wire. So packet 3 is going to interrupt packet 1. Shortly after that, in comes packet 4. Well, packet 4 is on VL3, which is another packet that is MPI or latency sensitive. It's going to follow right behind packet 3. At some point later, packet 5 comes in, and as you can see, packet 5 is going to go ahead and interrupt packet 1, and then eventually packet 1 is going to continue to move on and be put out on the wire. Packet 2 would have come in, but it's also a large message. It's going to wait until packet 1 is completed. It's a lower priority packet. At a later date, in comes packet 6, the yellow packet on path 4. It's going to go ahead of packet 2, but after packet 1 is done. So this is an example of the traffic flow optimization where the preemption is going to enable bandwidth fairness and also a very, very deterministic latency for these latency-sensitive packets. In Intel, in the labs with live equipment, they ran some experiments to verify how does this really perform. So they ran the first experiment they ran where they did traffic with only MPI latency-sensitive traffic and normalized it to a 1 just to set kind of a baseline. They added in, while they were running the MPI traffic, they added in the bulk traffic and bulk storage where they had large packets, and they measured again what the latency was for the MPI traffic. And as you can see, it varies quite a bit, and it normalizes and as an average is much higher. So the range is on the kind of the low end. You can see on the low end, the MPI message would have arrived at the TBUF when the large bulk traffic was almost finished. It didn't have to wait very long, but if it arrives in the very beginning, it's going to have to wait a long time for that packet to complete. And you can see that it brings you a much higher numbers. So when we turned on the TFO feature with the bulk traffic, you could see the latency for that the MPI compute traffic dropped to just above what it was as if you weren't running the bulk traffic. So if you look at all three of them, you can kind of see the normalizes, the blue, the green is with TFO on, and the orange is with TFO turned off. And there's so this is an example of actually confirming the feature works as advertised. So if I move on to congestion management, I'll go through this briefly. As I said earlier, the egress ports have VL work FIFOs, and from those workload FIFOs, we can calculate how many packets are waiting to be transmitted per VL, how many flits, what are the wait times, Q wait times for the VLs. We have congestion delid counters, along with utilization counters. We have a series of counters and machinery at the egress port that will help monitor and track what's going on for that particular port. With this information, we're able to identify whether the port is a victim of congestion or a root of congestion. And based on configuration for the FECN, we're able to mark packets based on size of packets and certain metrics. We're able to mark packets and do the FECN mechanism. We have a medium grain adaptive routing mechanism we call MGAR, and that is the ability at a switch level independently. Each switch independently is pre-programmed with alternate routes for certain delids and for the port itself. So based on congestion information that is maintained at the hardware level and works with the firmware, the firmware is able to alter the delid paths for certain packet streams in hundreds of milliseconds or every second, based on what the state is and what the congestion is, without any software intervention. This analysis is going on independently at each switch continuously. As I said earlier, the hardware mechanism partners up with firmware to do this delid altering at programmable rates. By allowing the selected packets to circumvent the congestion, the adaptive routing, we end up getting a better utilization at the Storm Lake network and increases network performance. I'm going to move into the platform area where there's some challenges with the Omni-Path platform design. How do you implement a 1U top-of-rack switch with 48 ports coming out of the faceplate? And then also implementing it with 25 gig channels, enabling 3-meter direct attach interconnect. And we're trying to do this without using embedded redrivers because of the added power. We're trying to not do it with FEC because of the latency penalty. And then we're trying to achieve a bit error rate of 10 to the minus 29, or 3 times 10 to the minus 29. And we're able to use that, achieve that with the OPA link level retry or packet in protection. These same kind of problems occur when we go to the director class switch, where we don't want to use embedded drivers inside the director or outside, and we don't want to require FEC and also achieve the same bit error rate. So the Omni-Path Edge Switch 100 series has 48 ports, 100 gig per port in a 1U, 100 to 110 nanosecond port-to-port latency. This was achieved by an innovative dense packaging where there's 3 rows of QSFP 28s, which achieves the 48 ports at 100 gig. And also, if you see in the diagram, there's a recessed faceplate, and that minimizes the PCB trace loss for the ports that are recessed because of the switch ball to faceplate. The trace length is less. We're able to achieve excellent signal integrity and improve the cable length, which enables us to support a 3-meter cable at 30 gauge and a 5-meter cable at 26 gauge for copper cables. There's no retimers on any ports. There's no FEC, and there's no retimers inside or outside. So if we go to the director class switch, there's the 20U director class, which is a giant switch, 768 100 gig ports. And then there's also the 7U 192 port, each port, 192 ports with each port being 100 gig. Now we can scale from a 7U up to the 20U at 32 ports increments. And this is these director level class switches are two-tier switches where the latency varies from 300 nanoseconds to 330 nanoseconds. So there is a variance of the latency. As I said earlier, there's 100 to 110 nanoseconds latency, and that has a lot to do with the physical distance from one port to another within the ASIC itself. Ports that are close together, you get the lower numbers. Ports that are corner to corner, the latency is a little bit higher. Again, with a director class, there are no retimers. The internal and external paths are all no retimers. There's no FEC. As I said earlier, we're trying to achieve, and with the director class, we're supporting the 3 meter 30 gauge, 5 meter 26 gauge. There's no optics or retimers. So there's, if you look at the top of rack switch, or the two chassis in one rack, that comes out to 307 terabits per second aggregated bandwidth per rack. Now, if I go into the bandwidth, latency, bandwidth, and message rate, and that's kind of the key metrics for the fabric to kind of indication of how good your fabric is. This is a slide from one of the marketing decks where they did some benchmarking, and for a couple of different processor complexes where there's 18 cores running at 2.3 gigahertz or 22 cores running at 2.2 gigahertz. And the latency, for a one-way switch is 910 nanoseconds, where, as I said earlier, the switch is responsible for 100 to 110 nanoseconds. It's fairly consistent between the two different processor complexes. We're able to achieve the bandwidth of a 12.3 gigabytes per second, which is slightly lower than the 12.5 theoretical max. And then for the bidirectional, we're able to achieve 24.5 gigabytes per second, which is slightly below the theoretical max of 25 gigabytes per second. So if we go to the bidirectional message rate, for the 18 core, we're able to do 137 million packets per second, roughly. And as we scale to the 22 core, we're able to get up to 172 million packets per second, where the switch is capable of supporting from a port to port of 195 million packets per second. So we're slightly below that with some overhead within the switch, and so the number will normally be driven and dictated by the processor complex or the HFI. So that is my conclusion and summary of the Omni-Path Gen 1 switch and platform architecture.
Thank you very much. We have time for a few questions. Please come to the microphone, state your name and affiliation. You'll start on the right here.
Yes, Brian Holden, Can't Do Bus. This looks great. I noticed you use 28 gig SerDes everywhere, and one concern that I have on the 56th generation of SerDes is that they need big FECs to do anything, and on these long-reach SerDes. And I was wondering if you could give some insight of what you had in mind for these kind of protocols where they're very latency sensitive going forward.
I didn't quite pick up there's a lot of echoing.
56 gig SerDes, the next generation of SerDes need large, high latency FECs to do anything, right? And that sort of breaks these request grant protocols. And I was wondering if you had any ideas of what sort of steps you might take going forward.
So for the 56 gig SerDes, you're right. The link level or the packet integrity protection needs enhancements, and that currently that is being worked on the next generation. So there are going to be improvements in that area. But it's a current enhancement and working on for the next generation. I can't go into details of what those are, but you're right. What we currently have from Gen 1 will not work for Gen 2, so there are going to be enhancements and there are improvements to go after that problem.
Great, thanks.
Ken Chen from Xilinx. You're quoting the error rate after retrial is 10 to the minus 29. So what is the error rate without the redriver, without FAC, without anything? What's the raw error rate?
10 to the minus 12.
10 to the minus 12? Okay.
Yep.
Ramesh, Synopsys. Do you have a number for like something like MPI all reduce over the rack if we are using this switch?
I don't have those numbers. Those are in the marketing deck. And some of the marketing decks, they have a lot of performance and numbers and performance numbers in that particular. But off the top of my head, that's kind of out of my area right now.
Okay, I'll check.
Thanks.
Dipankar Acharya from Cisco. You talk of the rerouting, MAGR or something you call it, I forget. How do you avoid or manage any reordering of packets in the process?
All the packet routing, if I get the question right, is all predicated on in-order routing within the switch. So there is no dispersive or no kind of, if that's what your question was, it's all in-order routing.
What happens when you change the route, which is, I thought...
Oh, if you change the route, what's going to happen is the end-to-end CRC is going to fail, and there's going to be kind of an end-to-end retry. So that's why you've got to control how often you'll do congestion. So there's certain metrics that we keep track of to monitor how often we want to do it, and based on how big the fabric is and how kind of long-lived the congestion is.
Thank you.
Subbarav from Cisco. A couple of questions. What is your buffer size per port? Input buffer size, packet buffer. Input buffer size.
How big it is?
Yeah.
The input buffer size is 256 kbytes.
Okay. And the second one is if there is a congestion, you're going to send some kind of ECN back to the source. When that scenario, what will be your message rate? Obviously, it will come down somewhat, right? Your number of messages per second in the congestion case.
I'm not sure if I follow the question.
So if the switch has a congestion, egress congestion, you're going to send a ECN packet back to the source to reduce the traffic, right? So in that scenario, what is the message rate per second?
So the message rate per second with ECN.
Oh, the message rate is unaltered. When we turn on the packet integrity protection, that's running behind the scenes at the link layer. So that's not going to alter latency. That's not going to alter the packets per second performance. It's running at a link layer like a layer 1 or 1.5.
No, but you have a congestion. You cannot maintain the line rate, right? You're going to come down some kind of reduced line rate on the messages because the source has to receive the ECN and they have to back off. In that case, you can't maintain the line rate.
We can get to if you want to talk, I can talk afterwards. That'll be easier. If there are questions about the platform, Vladimir Tamarkin is the lead architect. He has a far more knowledgeable on the whole platform and some of the innovative things they've done at that level.
Okay. If there are no further questions, let's all thank James for a great talk.